Hello, today we're going to be talking about Qi, scaling microkernel capabilities in cache-incoherent systems. This is work mostly done by Yuxin. I am presenting Gabriel Palmer, and this is work done in collaboration with Dehan Malochikik at Hewlett-Packard Labs. So what we see here is a breakdown of a system into two different dimensions. On the left, we go from single node systems up to distributed systems. And in between, we have something that I'm labeling with single system images, SSI, as a type of system that provides an abstraction of being on a single node while actually being on a more distributed system. In the X direction, we have memory coherency or non-coherency on the right. So if we have ever-increasing scale of data that we need to process, therefore larger and larger systems, if we have a single node on the bottom left, we really only have vertical scaling, which of course is limited in its capacity. When we go to accelerators, we start to see that oftentimes they're still run on single node systems, though many times they're connected together, and they start looking like non-coherent systems. So sometimes the accelerators will have their own memory that's completely separate from the core systems, from the CPUs. In the top left, we see something that I'm loosely terming as data structure consistency. We, on a distributed system, don't actually have memory coherency, but operations like Paxos and Raft will try to make it seem like replicated data structures actually do have some consistency about them. So I'm using the term coherency and consistency as somewhat related. However, in the top right is the most interesting set of systems. We have the modern push into disaggregated memory, the idea that we can plug in and pull out memory into systems completely independent of the computational units is disaggregated memory. And we think about that in many different ways. If it is a strictly distributed system using NICs to communicate between the hosts, then often we're talking about RDMA to transfer data back and forth between the memory components. And we've been seeing the rise of rack scale computing additionally, which is the idea of disaggregating memory and then using it as the primary system storage. So replacing archival disks or SSD with actual non-volatile memory. And the issue with this is that a lot of this disaggregated memory scales to the point where having coherency over it becomes very difficult. So a lot of these systems are non-coherent. The question that we're going to be investigating is if there is a capability to have an operating system that can span across an entire system of disaggregated memory, therefore providing a single image, a single notion of access control, and sharing to all of that memory while still working for non-coherent memory. So this is how we kind of think about a system. On the top, we have 4 computational units. They might have a relatively small amount of memory associated with them, and each of these 4 units is running, in this case, 3 processes each, and they're connected via some sort of an interconnect to massive amounts of DRAM or NVRAM, depending on what we're talking about. Now, one way of putting an operating system into the system is the traditional way, and it's essentially just saying, all right, let's take an operating system, boot them separately onto each of these individual systems, and we have something that looks like this, a number of operating systems that somehow need to coordinate for all of that shared resource of the memory. And a lot of these operating systems have the bare minimum of support for being able to do that, so long as that NVRAM or the DRAM can appear within the physical memory of each of those nodes, then we can use hot-swappable memory to be able to access it. So here you see each of the operating systems being given a different range of the NVRAM. Now there's a question of who should actually decide this access. Who should decide which operating system, which system has access to which ranges of memory. And of course that gets a little bit more complicated indeed when you start sharing between those different operating systems, truly requiring a coherent and interesting access control policy. So the question is, once you start having systems like this, how do you deal with access control? How do you decide who gets which ranges of memory? How do you balance the memory dynamically between the different nodes? And how do you decide to share or not share between the different nodes? So this is a difficult question when you have a lot of different operating systems that are all trying to share the same memory. You're going to need often some level of indirection that can make list mapping and provide this access control. However, a different path is to take a single operating system and make it span across all of the systems. So in this case, you can see that the operating system's data structures themselves are placed within that disaggregated memory. Therefore, it can use its own data structures to track which node should have access to which ranges of that disaggregated memory. So we can use the operating system itself and its own tracking structures itself to decide what of that disaggregated memory should be shared, should be global, etc. What are the access control policies that wrap over it? Now, of course, any realistic system is going to have some sort of a split between the local memory, which might or might not be accessible to other nodes, and that is global. So the operating system will need to support having some of its structures that are local and some that are global. As you'll see, our policy is simply to never have a pointer from the global to the local. Now, the interesting thing is that if we have a normal system, then we have something that looks like lists. We have a process that has its own page tables, the purple process on the far left, that has its own page tables that are now in local memory. This is a typical process in any conventional system. However, if you start placing the process's page tables and all of its operating system auxiliary data structures within the shared disaggregated memory, now you can actually start running that exact same process on each of the nodes. So I have the dotted lines here to designate that those are essentially the same process, the same page table structures, the same access control, the same memory, etc. And now if on any of the nodes they want to access some of that global state that spans the entire system, they can do so safely by simply IPCing using an inter-process communication to talk to that one process that spans all of the system. However, as nice as this might be to have services that are locally accessible, therefore not requiring any interconnect work in addition to kind of loads and stores, on practical systems, this is relatively complicated. It's relatively complicated because of the non-coherency that we'd actually have within this disaggregated memory. A lot of people are talking about that memory being non-coherent simply because of its scale and its dynamic properties. So if we have one node, in this case the one on the left, that does a write to some variable within those data structures for the process, and we have another node that is perhaps running that same process that does a read, there might be cases where that ends up working. It might be that that process will now read from the disaggregated memory, do the load, get the one, and we have a kind of consistent value for that variable x. However, if that variable was previously read into the cache of that second node, then a hit within that cache might result in some incorrect value, in this case 0 being returned from the read. So this is of course just saying that these caches are not kept coherent at this scale. So this is the fundamental challenge for an operating system that wants to have access control policies that can span the entire system. How can we have an operating system that can operate in non-coherent memory to be able to provide its own policies, its own processes, etc., that can span all nodes? Now, there are some trivial ways that we think about programming for non-coherent systems. So the most simple is that each range of that memory in disaggregated memory should have only one owner. Therefore, we should partition the data structures. In that case, coherency doesn't matter because you're never sharing cache lines between separate caches. No sharing means no coherency necessary. However, when we want to access some variable that is perhaps held on a different node, we need to always go through communication. Now, supercomputers are very used to doing this, right? We communicate between nodes all the time. However, on disaggregated memory systems, we have the potential to have load store that's exceedingly fast, spanning the entire system. So it would be nice if we could maintain that if there are performance benefits to be had. Now, another approach is, of course, to have replication between each of the nodes. Again, partition memory, but logically have the same data structure replicated across multiple nodes. So we might have two-phase commit to actually make modifications to the shared data structure, and we have message passing-based coordination on modification. So the benefit here is that if all that we need to do is get some value or query the shared data structure, then all that we need to do is speak locally to the version that we have on our node. However, updates become pretty expensive. So this work does some preliminary investigations of an operating system that we call Chi, and it's an operating system for disaggregated memory. It has non-coherent data structures, and the operating system can work within the bounds of being non-coherent. Yet despite that non-coherency, it does have global capability-based access control to manage all of the memory on the system, what should be shared, what should be allocated to which node, etc. So a side product of this is that it enables local access to shared protected components. We can locally access global state within that operating system instead of needing to talk to another node for it. So the high level of how we do this, and I'm not going to go into all the details here, is that we use a system that we call bounded incoherence. So when we want to share non-coherent memory, as is default for a lot of the operating system's data structures, we need to have load store coherence that is ensured within a bounded window of time. This is to say that I might have a non-coherent cache for a certain period of time, but after that amount of time, I can be guaranteed that it will be updated to a coherent value with what's in memory. So that's where this bounded incoherence comes in. We also assume that there happens to be an in-memory cache operation that we can leverage. So how do we do this? There are a few assumptions that we make, and we implement the operating system around these assumptions. One of them is that we essentially update our synchronization. The update synchronization is limited to effectively a single compare and swap using that in-memory cache. So when two nodes need to coordinate with each other to allocate some resource, they need to effectively serialize the entire operation, the entire synchronization into a cache. So the API for this starts looking pretty similar to read, copy, update, if you are familiar with that. And this has a strong preference for kind of lock-free data structures. And when we do modification, we're essentially saying, yeah, you probably need to make sure that you either do not update data often, or you update it only with that single compare and swap. Now, how is coherence performed? If we need this bounded incoherent guarantee that every amount of time we get to see coherent data, then we ensure that at the operating system level by providing periodic flushes of the access data within the cache, forcing coherence by essentially flushing out periodically that data that needs to be flushed out. And because we are periodically updating the cache, forcing us to go out to memory, this effectively means that we cannot reuse freed nodes, freed memory within the operating system until some sort of a period updates our storage. And the intuition behind this, I'm not going to go into it in detail, but the intuition behind this is effectively that if we have two modifications to a range of memory from two separate nodes, it's quite easy for those updates to start to become incoherent. So we ensure that all of the updates need to be serialized with a single cache, and that we only have one of these updates effectively per period. Therefore, if some node had read in the data, it will have a version of the data that at one point was correct up until the periodic flush. So what does Qi look like? Well, Qi is a microkernel that's based on the Composite component-based operating system that we've been developing for a long time. And Composite is a capability-based operating system that uses capabilities to define its access control policies. One of the primary features that made Composite interesting for this work was that it's effectively entirely weight-free. So all of the operating system data structures use weight-free synchronization for coordination. Note, they do assume a coherent system, so I had to change the core of the system significantly, but at its core, it provides lock-free synchronization and therefore works slightly easier with non-coherency. It provides very simple operating system abstractions like threads, IPC endpoints for communication between components, where components are a capability table and a page table effectively put together. They are the protection domains within the system that limit access to different resources, including the disaggregated memory that can be accessed through the virtual memory. We include frames, which are untyped memory that we can use as building blocks for different pieces of the system. And additionally, we have other forms of synchronization like asynchronous communication. Let me just go through a very brief example of what it's like to actually have an operating system within this kernel and how we've modified it to work with non-coherent systems. So on the right, you see that we were in user level and we've made a system call to a system call something like component create. Component create has access to the current capability table of the current protection domain, the current component. The capability table includes all references to resources that we have access to, except for memory. And if we look at the code, what we're effectively doing is we're saying, okay, I'm going to look up in the current capability some offset, and I'm going to try to create a component at that location. And what this code is saying is effectively that it should create a new component at that location in the capability table using the page table and capability table that are effectively passed in. So we offset until the capability table, as you see on the right, and we notice that the slot within this capability table, the storage within this capability table, has a header that is teal in the diagram. And we use a compare and swap, in-memory compare and swap, to change that header from 0, which means that we can actually use it, that it's not currently used for anything, to a reserved value. So while that slot has reserved as its header, it cannot be used by another node for anything. It cannot be accessed by another node. Now, it could be loaded from, of course, there's nothing to stop that, but the kernel's logic will prevent it from being modified or used in any useful way. And at that point, after we've reserved the slot, then we populate it, we make any modifications we want to it, we put our data inside of it, this puts our page table and capability table into it, and after that point, we want to make it accessible and usable by not just this node, but by all other nodes. So at that point, this component that's currently active using this capability table would be able to access that component on all nodes. And it does that by simply marking it active within its header and then flushing out or doing a write back of all of the data within that slot. So this effectively means that all of the other nodes will either be able to reserve and use a slot or not access it. Once a slot is prepared and accessible, then it is atomically accessible by all of the nodes. So this kind of a brief protocol illustrates how we've modified the system to work within a non-coherent constraint. The CLWB is there to ensure that the backing data is accessible, but you can imagine there are other operations within the system whereby we need to look up things in the capability table and use them, but not necessarily modify them. In those cases, we do not want to do CLWB or cache flushes as we walk through the kernel's data structure, because that will make the fast path of all of the kernel's operations exceedingly slow. So we want to access in cache all of these data structures where possible. So what does this do? This effectively means that this previous case that we looked at, where one node on the left has written out to X and then another node tries to read from X, that actually is still possible. We could try to read from the capability table and find the previous values in it. If we find that there's an empty node, then we have an optimization to flush the cache lines and go out to memory, but this is a rare operation because normally components don't access empty slots. They only empty useful slots. So it's possible that we'd read 0, but after a certain amount of time, we would flush the cache using the bounded incoherence flushing of the cache, and at that point, we would be able to read back in that value and be able to access it correctly. So this notion of periodically flushing the cache is integral in being able to ensure that all of the nodes will see a coherent version of that data. And the goal of the system, the operating system, and the periodic cache flushes that are added into the system is that they limit the shared data structure modifications to essentially the modifications, I should say here. Yeah, the modifications to once per flush period. And that means that there's no modification ambiguity where one node has modified one of the data structures and then another node tries to do the same, and then which node has the correct cache contents. There's no ambiguity here. You might have a stale cache contents, but that's only for a limited amount of time, and then you have the updated value. So there are a lot of implementation details for how we implement this periodic cache flushing in an efficient way for the kernel's data structures. The high level, I'm going to point you to the paper for details there, but the high level is effectively that each node flushes its cache periodically, but if we were to do that for the whole cache, it's very, very expensive. So it can walk through its own page tables to look at the access bits to only flush those pages that it accessed. There are some additional considerations that get pretty deep in the weeds for page tables and TLBs that I'll not go into here. And I want to point out that we actually don't address within this paper how user level components might maintain their own coherence within that global memory. However, the bounded incoherence work, which is the previous publication, does talk about that, and we use that work to implement Memcached in a way that uses non-coherent memory. So how can we use this? The operating system in this case, it could implement a shared service, for instance, a shared key value store like Memcached, and if that needs to be protected from all of the applications on the system, it could be implemented on the left as circled here in a separate process that runs on every node. And we can see that its memory exists on multiple physical ranges of disaggregated memory. And if processes need to access Memcache, they can do so locally through IPC. Another architecture that might be appropriate for some systems is that we have the key value store be a library that we can actually load into a process, and then it can access that memory directly. So this is a trade-off between kind of protection and performance, and the operating system will be able to make the access control decision for this. Now, in both the left case and the right, we have a situation where we're optimizing for fast access to the shared memory. But that effectively only really works for GET requests in this case. So if we want to get a key X, then it can be very fast because both of the nodes on the right can get it locally. This applies to the nodes on the left as well. I just didn't draw the arrows. However, if we want to put some variable, in this case X, each of the variables needs to be owned by a different node. So we do partitioning of the data structure for puts, but not for gets. So we're leveraging the fact that we have very fast load access and cached access to all of the data structures within disaggregated memory, but to make user-level sharing and modification of those shared data structures easy, we do partitioning just for the modifications. If we look at how this actually pans out, we see on the left we have GET request latency, and we have thousands of cycles per operation on the y-axis in both of the graphs. We're comparing against two-phase commit, which is doing replication of the data structure, and we see that the red portion of the overhead is the actual hash table itself, so that's relatively constant across all of these. We have message passing that needs to be used in two-phase commit. We have message passing for partitioned as well, and we have system call overheads to be able to actually access things using IPC and whatnot, right? In the case where we're using Chi, we have these two examples that we talked about here, the process-based version on the left and the library-based version on the right. And what we see now is that we have IPC between separate processes in green, adding some additional overhead there. But the GET requests are significantly faster on Chi simply because we can directly do loads from memory. And then if we need to do stores, we need to modify, we see the put requests on the right. And we can see that two-phase commit has some additional overhead for the two-phase commit protocol. We can see partitioned has all of the overheads that are effectively identical to what they were on the left for GET, because we might have IPC that we need to use to go in between the different nodes. And then for Chi, we have some additional overheads for the hash table because we had to modify it to be a read copy update style hash table, which is more expensive on updates. We have some message passing. As I said, we partition on put requests, and we have some cache flushes because we need to make sure on a node that when we make a modification that that data gets written back into the disaggregated memory so that updated value can be read elsewhere. Now again, we are not talking in this paper about the consistency at user level, so we're using relatively straightforward ways to achieve that here. Now, if we look at the impact of this, when we look at the throughput of the system, we can see that the library version of Chi can get upwards of 250 times 10,000 requests per second, versus the two-phase commit and the partition that are all at about 50. Now, of course, that's with a very low update percentage. If we have a higher update percentage, then we start having the additional costs of needing the communication and coordination in Chi, and you can see that that goes down with update percentage. But even at 50%, we maintain better performance than a lot of the other options. Chi, when we don't trust the data structure enough that we don't trust the client with direct access to the data structure through a library and instead require a process for that. You can see the IPC overheads on the system are significant and take us from 250 down to about 100, and we go down from there. But this is a viable option for being able to store global policy and global data across all of the nodes while maintaining some consistency between them. So in summary, I've introduced Chi, which is an operating system for non-coherent shared memory systems. It provides full system access control across the entire range of incoherent disaggregated memory, and it leverages our simple weight-free composite kernel. You can see the link for that down below. And it uses bounded incoherence for some version of coherency in the system by periodically flushing the cache to have a guarantee on when we will see updates. So I hope you enjoyed this. If you have any questions, please reach out. Thank you very much.